the quiz, the last quiz. If you have any questions, I can address it. If you want to, also, if you don't have any more questions, then I will go over the notebook that I uploaded on Blackboard, which you will mainly be using to solve the second homework, which is about building histograms. Okay, so I already prepared kind of a tutorial using Python notebook to kind of build the how to build a differential privacy mechanism and how to use it in case you have like other databases. Okay, so just one one thing here. You see, because we are a little bit behind the original schedule. So again, as I said, today, oh, actually, today is 25th, and 27th, there will be no class. Okay, so it's next Tuesday, no class, kind of as a substitution for the time we'll take from you on Thursday for the midterm exam. Next week, inshallah, which is week 10, we're going to start a completely new topic. So we are shifting our attention now into what is called cryptographic data privacy. So what I mean is that we're going to use cryptography in order to preserve the privacy. So we will talk about something called homomorphic encryption, and then we'll talk about secure multi-party computation and secure data outsourcing, previous transfer. We'll talk about data hiding and steganography, and we'll also talk about, so all of these are kind of data processing or cryptographic solution for privacy preserving data processing. And then we'll talk about privacy preserving data communication, how to communicate data while preserving the privacy. And now, if you notice that in the previous schedule, I allocated the last week 15, for project presentation. Okay. Now, since we are a little bit behind the schedule, so I thought maybe we can do the projects offline. So you can just I'll meet with each team individually, and then I will have like you're gonna present your work to me instead of presenting it to your in front of your colleagues. And then we're going to utilize that time to talk about two kind of applications of privacy enhancing technologies. We'll talk about the hardware if we have time, and then we'll go back into our, if you remember, we discussed in the first 2 to 3 weeks, we discussed the contact tracing application, right? So, and then we kind of contemplated about the privacy and utility aspects. Now, in the last week, we're gonna take kind of one class discussion or kind of an exercise to consolidate all the information or all the technology and techniques that we have covered in order to pinpoint the privacy concerns in contact tracing application. Now, how can we fix it using the technologies that we learned? Okay, so this is just, I thought I draw your attention to the change in the schedule. As you see, we are supposed to have 5 quizzes, but we will fit one more quiz, which is quiz 6, and that quiz 6 will be optional, and it also like kind of be kind of a margin. So if you do like bad in one of the quizzes, then quiz 6 will be kind of basically we'll take 5 best of 6. Okay, so this is kind of like a caution for if you do bad in one of the quizzes. Make sense? Anything here? And by the way, this is, so I already released homework 2. We have 2 more homeworks. Okay, mainly one coming from the cryptographic encryption, and one coming from the anonymous communications. Okay. Right. So let us, I think most of you want to go over the last quiz 3. So again, the questions are kind of in random order. So I'll go over it one by one in this order. So the first question says, in group privacy, the neighboring databases can differ in K records, or actually differ in K records, right? And we said that if we have group privacy, then the probabilities are bounded by how much? E to the power epsilon or E to the power C epsilon? So let's go back to the slides. We go into the group privacy. It should be E to the power C epsilon, right? So this is the total budget. Now, if rather than having C epsilon or K epsilon, okay, just avoid, if we have only epsilon that we're gonna pay, okay, so in fact, we don't want the probability to be E to the power C epsilon. We want it to be E to the power epsilon, right? But we have the neighboring databases are differing in C or K records in this case. So the question is how much or how do we allocate this epsilon, the privacy budget, right? For each, basically you take E epsilon and divide it by K, right? So because we have K records different, then when we want to, each record will take exactly epsilon over K, and obviously that will achieve epsilon differential privacy. And this is a manifestation of what is called the budget, privacy budget allocation. Okay. In other words, you know, just like in any project management, you have an amount, a budget, right? Financial budget, and you want to, let's say, you want to build a couple of buildings. So how much each building does it cost, right? So you can allocate the budget on the, you know, like on the material, on the labors, and so you have to allocate the budget based on your project. So similarly here, we have a budget of total of epsilon, but the database is differing in K records, so each must have K epsilon divided by K. Okay. The second question says differentially private histogram is built using parallel queries. That is true, and I already mentioned that maybe at least 2 to 3 times. We said that, you know, since the histogram that we deal with works with non-overlapping bins or buckets, so then we can exploit the parallel composition queries in order to kind of limit the, you know, like the privacy budget. So the overall privacy budget would be the maximum of the budget of each mechanism, right? Okay. Any questions so far? Right. Third question says if you have two mechanisms, A1 and A2, which are 0.1 and 0.3 differentially private mechanism respectively. So A1 is 0.1, so epsilon for A1 is 0.1, and epsilon for A2 is 0.3. Now assume that the A, which is kind of the overall mechanism, is a sequential composition of A1 and A2. So A, in order to run A, we have to run A1 and then A2. So this is kind of the sequential mechanism. What is the total budget for A?
Sum.
That's sum. Okay, 0.4. Okay. Question 4 says, which of the following is not an epsilon differentially privacy mechanism? Differentially private mechanism, sorry. Is it type? Obviously, it's K-anonymization. Differential privacy provides privacy guarantees for a specific individual database. Now, there are a lot of kind of, you know, like question or confusion about this particular question. Now, yes, true. It is, you know, differential privacy is designed, okay, with the intention in mind that it should preserve the privacy of an individual, right? But not a particular individual. We are looking for to preserve the privacy of all individuals in the database. And that is stressed or expressed by removing every record. So the neighboring databases is not about, you know, removing 1 or 2 individuals who are we really interested in preserving the privacy. No, we're gonna remove all records that belongs to all individuals, right? So in fact, that if we come back to the definition of differential privacy, right? So this bound should hold not only for individual A or B or C, no, in fact, for all individuals. Let's say if we have n individuals in the database, so for all of them. And that's why, you know, in the definition we say for all neighboring datasets. Okay. So the answer to this is not really a particular individual, but we're looking for all Here is the keyword. A specific individual. No, it's actually all individuals in the database. And how to do that? By removing one record at a time from all neighboring databases. To form all neighboring databases. Okay. So the question 6 is let A1 and A2 again be 0.2 and 0.3 differentially private mechanisms respectively. Assume that A is a sequential composition of A1 and A2. So what is the total budget for A, mechanism A? Because it's sequential composition. 0.5, right? The trick here is as the following. Now the trick here is as the following. We know that A is composed of two mechanisms or sub-mechanisms, let's say A1 and A2, right? So in one, we get some value. After running A1, we're gonna get some value. After running A2, we're gonna get another value, right? If we take those two values together and take the average, does that reveal any more information about the overall mechanism? In other words, what privacy guarantees do we get if we take the values of A1 and A2 and average them together and get a single value? Does it give us any advantage or any information about the individuals in the database? In fact, no, because post-processing property says even if you take any output, right, do whatever, apply whatever function that you want, the privacy budget is still the same. So if you have a mechanism A, which is 0.5, differentially private, you take the output, average them, sum them, whatever you do on the values, the budget is still, or the mechanism is still 0.5 differentially private. Okay, so it's not a matter of taking the epsilon1 and epsilon2 and average them to get 0.25. No, it's actually kind of exploiting the post-processing property of differential privacy. Any question here? Okay. Question 7. The noise added by a differentially private mechanism does not depend on, of course it depends on the privacy budget, E, epsilon. Of course it depends on the sensitivity of the query, because basically the variance is the variance of the lambda mechanism, Laplace distribution, should be GSF, or the global sensitivity of the function, divided by epsilon. Now, the probability distribution of the added noise, of course, because again, we are sampling this noise from a probability distribution. And in fact, and I didn't tell you that, in fact, there is another mechanism called Gaussian mechanism. And what do you think the difference between Laplacian mechanism and Gaussian mechanism?
Isn't Dr. Gaussian is normal distribution?
It's a normal distribution. So the noise itself is drawn from a normal distribution, or normal distribution is actually a Gaussian distribution with mean 0 and variance 1, right? So normal is a specific case of Gaussian. But to be in general, we refer to any bell shape distribution to be Gaussian distribution. So rather than drawing a noise or sampling a noise from a Laplacian distribution, we sample it from a Gaussian distribution, and we get ourselves another mechanism called Gaussian mechanism. But that is not really, Gaussian distribution is not really, I would say, common because it has so many things. The main thing is that, like Laplacian distribution, it tends to have kind of a peak or kind of spike on around the mean, which is a better property than the Gaussian one. Anyways, this is kind of technical details you don't have to worry about. And question 7. Yeah, so probably so the answer is the size of the table, and that is I already also kind of explained this, because I said differential privacy does not care about the size of or how many neighboring databases do we have, right? It doesn't care about n. It is just in the definition that you need to worry about every neighboring database, no matter how big is that. Obviously, if we have a bigger table, that means it's the better the privacy, but differential privacy will guarantee, the same amount of privacy regardless of the size of the table. Question 8 is a little bit straightforward. If we have A1 and A2 with 0.2 and 0.3 differential privacy budget respectively, what is the value, or what is the overall budget for A? The maximum, which is 0.3, right? And the last question, again, I received a few questions, but you know, I answered this very question during the class, okay? And I said, you know, like, especially when I showed you that notebook, I told you, you know, the plus mechanism can also return a negative noise, right? So if you add positive noise, that's simply addition. If you add negative noise, that's a subtraction. So in other words, yes, the answer can go up, or can, you know, actually can be reduced. Okay, so it is true. Let's see, how did we do? Okay, so any questions about the quiz?
Doctor, for the last question, I don't see the relation between being minus and the question. I didn't understand it.
Okay, so the correct answer, the correct answer for the query without any mechanism, without any noise, is actually 3. So suppose that we are asking about how many employees that earns greater than 30K a month. Suppose that the answer, the true answer of the original table is 3. My question is, if we apply Laplacian mechanism, can we get an answer of less than 3? So for example, can the answer be 1?
Yes.
Why?
Because it can be negative.
Did that answer your question?
Okay.
Okay. Right. Any other question regarding the quiz? Right. So in fact, you know, before I move on, I think I have left some few slides in lecture 9, and really lecture 9 really will be in your included in the midterm exam. But what I think I already made an announcement for you. You can exclude all the slides from 5 all the way to 18. Sorry, 5 to 17. Okay, so from 5 to 17 basically they are only a kind of technical details about the exponential mechanism and as application. So remind me, please, did we go over all these slides last time?
Yes, Doctor, I did.
Okay, how about this max response?
Yes.
How about the k-means problem?
Yes, also.
Okay, but then that was the last thing, sir. Okay, so let me, in fact, let me just skip or not skip, since we already covered it, the kind of what do you mean by exponential mechanism and max response. Let me go over a little bit k-means algorithm problem, sorry, and how to make it differentially private. And why I wanted to kind of express this again, because you know, if you go into the literature of differential privacy, most of the practical usage of differential privacy comes with machine learning models. Okay, so if you go, you know, like just Google some privacy and machine learning, you will see a lot of machine learning models that are actually differentially private. For example, k-means, differentially private k-means, differentially private deep learning models, differentially private SVM, differentially private linear regression, and so on. Okay, so in fact, you know, differential privacy, because of especially the Laplacian mechanism, because it's kind of, I would say, easy to achieve, it can be integrated with a lot of kind of mathematical models that are built or that are used in machine learning. Okay, so let me go over. So it's worth to understand how can we apply differential privacy on machine learning models by taking a very simple example, which is the k-means problem. So k-means problem is an unsupervised machine learning model that basically, if you give it, so you are giving some points, okay, and to be kind of, you know, like formal, These points are kind of given given as x1, x2, and xn, where x1, x2, and xn, think about it as, you know, 2 dimensions, 2D dimension, okay? What we want to do is to cluster these points or group these points into k clusters, okay? And that's what is called k-means or k clustering. Why it's called k-means? Because each cluster should be represented by 2 things: the mean of that cluster and the size of that cluster. Because you see, if we represent a cluster with its mean, then what we can do is we compute the distance between each point. So the points here, the white points, are actually these x1, x2, xn, right? And we are representing it in the 2-dimensional space. So if we want really to form a k cluster out of these points, what we can do is we can represent each cluster, each group, with just the mean point that comes in the middle. And how to compute the mean? We use the Euclidean distance, okay? So basically, the distance here is the difference between x1 and x1 of the center and x2 and the x2 of the center, square it and take the square root of the sum. Okay, so you can apply any Euclidean, the non-Euclidean distance in terms of, you know, vectors and so on to compute the distance. Anyways, I don't want to go into the details, but in fact, you know, you see, so this is basically what is k-means problem is, right? Why, for those who doesn't know, for those who knows, that is fine, okay? For those doesn't know what k-means problem are used in, suppose that you have a set of people and you want to cluster them or group them based on their, let's say, you know, like based on some attributes or kind of features. By features, I mean, you know, kind of characteristic that characterizes these people. For example, their age, their gender, their I don't know, marital state, whatever, right? And you want to group those people into groups, categories that explains their medical health. Okay, that, you know, like the status of their medical health. Those are, you know, like kind of healthy. Those are kind of have chronic diseases, some, and so on. So once you identify those group, then you're gonna build your, let's say you are an insurance company, you're gonna build your plans, premiums. So for example, for those who are healthy, it makes sense that they pay, you know, premium that is lower than, let's say, those with chronic diseases. Okay, so it has its own application, not only for, let's say, health insurance, but it can also be for car insurance. You know, you categorize the drivers into groups. Those are, you know, like safe drivers, especially, you know, like above some ages. Those are reckless drivers, and so on. Right. So you can, again, you plan your car insurance premiums. So it has its own applications. Now the problem is that, you see, the fact that I tell you my information in order to group me in certain groups, that by itself will breach my privacy, because I have to tell you what is my age, what is my, let's say, income, what is my, how many children do I have, all this kind of private information, right? But again, it's from utility point of view. If I was categorized on the right category or in the right group, right, then I'll pay, let's say, the optimal or the best amount of let's say insurance. So again, I'll get some utility, but I don't want to, you know, like share my information with company A or B or C or whatever, right? So the question is now, how can we provide you with this utility, which is, you know, like grouping you into the right group while preserving your privacy? So you don't have to kind of share your information, or even if you share your information, it will be used in a private way. Okay, so this is kind of motivation of using differentially private machine learning. So this is kind of the algorithm. So it's called a deep Lloyd clustering algorithm. Basically, you initialize random k centers, and then you repeat 2 steps. The first step is to assign each point to the nearest center, right? So basically, you see, you assign just random numbers. So the gray, the big gray point, the yellow, the blue, and so on. You are assigned it randomly. anywhere in the two-dimensional space, and then you compute the distance between every white point to the center. Okay, and then basically once you update, or actually, you know, if at some point you see here at the edge between the gray and yellow, this point, the white points, right? You need to compute the distance from that point to the gray center or the yellow center. The one with the shortest distance will belong to that center, right? So suppose that this gray one or the yellow one are closer to the yellow center than the gray center, so they belong there. And then you compute the set of centers, and you do that repeatedly until the algorithm is converged. Okay, so I would, if you know that, again, that is great. If you don't know that, I would really, you know, advise you to go and think on kind of start thinking about how does it work, because it has a lot of applications. Anyways, what we want to do is we want to turn it into a differentially private algorithm. And what can we do is we can take the same algorithm, right, and we just add noise, because that's what we do in Laplacian mechanism. So in order to turn a private k-means clustering into differentially private, we need to add noise to some output. And again, I told you the output of k-means algorithm is two things: the size of each cluster and the center of each cluster. So basically, we're going to add noise to those two things. Okay, so this is in a nutshell. Of course, devil in details. There are a lot of details that we need to worry about. For example, what is the sensitivity that we're going to add based on which we're going to add the noise at, right? And to answer this question, you need to start with some assumptions. You need to understand how the algorithm works. You see, as I told you, it's an iterative algorithm, right? So we need to set a number of iterations. Let's say that is t. And we have an overall budget, epsilon, right? So in other words, how many, or what is the privacy budget for each iteration? We have t iterations. We have a privacy budget of epsilon. So each iteration must take epsilon divided by t, right? Pretty much just like the question I gave you in the quiz. Now for each iteration, we have epsilon divided by t. And we want to add noise to the cluster. What is the sensitivity of the cluster size? I can tell you it's 1. Okay, so this is 1, and then we have another noise, or that is basically the computing the sum or the centroid, right? So what is the sensitivity of the sum? Remember, what is that in the slides? What is the sensitivity of a sum query?
The max.
The max.
Yes.
The max, right? So in other words, we have to make some assumptions. The assumption here is this square, right, is normalized. In other words, the length of this square is 1, with both in the height and the width. Okay. So what is the furthest point that we can add to this group? It's either on the corners, right? Right. So this one, this corner, this corner, this corner, or this corner. So in other words, what is the maximum noise, or what is the global sensitivity of the sum? It's basically by adding one kind of, if we're adding points to the corners, and in the worst case that we have another point here is the corner. So the maximum sum must be 2 in this case, because we have two dimensions, one the height, one width, and each height and width has a maximum of 1, maximum length of 1. So it's 2. So we have 1 plus 2, because these are sequential, we have 3. So each, the amount of noise or of the privacy, the global sensitivity for this should be 1 plus 2. So you compute in order to add compute that in order to know how much noise, or what is the sensitivity of the functions, right? That kind of control the noise that will be added for each iteration, for each operation. Okay, so this is, in a nutshell, again, this is the idea. You need to break down your algorithm, see what are the things that you want to preserve, the size, the sum, whatever. Add noise, but after, like carefully thinking about the global sensitivity of the function that you have in hand. Type. And so far we talked about, low level, or they call it low level sensitivity, like count, query, count, sum, and so on, and average. But there are also some, they call it high level sensitivity functions that are really, difficult to compute the global sensitivity for. An example for that is when we consider, this Netflix recommendation problem. And the Netflix recommendation problem basically is asking, if you watch movie A, if someone watched movie A, how likely, or how likely he will like another movie B. So if I like, let's say, for example, Braveheart, right? How likely I'm gonna like the other movie, Gladiator, for example? Okay. Or let's say if I watch Braveheart, how much do I like another comedy movie, right? So it must be lower than that. So these are basically the movie recommendation, and you're gonna do that for all users for all movies. And it turned out the answer to this question depends on four values: the average rating for all movies, the average rating for each movie, the average movie rating for each user, and the third thing is kind of a covariance matrix. If you don't know what is a covariance matrix, go and look. I'm not going to explain it. Go and find it. Now, you see, we are dealing with average. That is easy to compute the global sensitivity for. But when we are confronted with this covariance matrix, that needs a little bit of details. So I'm not going to go over the details because it's a little bit complicated. But see, the whole point here, the main takeaway point here is that you need to break, in order to make your algorithm differentially private, you need to break down your algorithm into the pieces, understand it carefully, and then apply the right noise to the right to the right function in your algorithm, and then you can claim that you have a differentially private algorithm. And of course, that has to be mathematically proven. Okay, so I'm not going to go over there because it's a little bit advanced. Okay, so this is kind of basically the privacy goal of any machine learning algorithm. So this is the slide that also included in your midterm exam. So whatever slides that I cover was kind of just for your information, which is what are the pros and cons for differential privacy. Okay, the most important advantage, right, is that it is proven, mathematically proven, that the privacy is guaranteed, not for one individual, not for two, for all individuals in your database. And that's why it's and probably that is also a kind of a disadvantage because it's a non-trivial mechanism. Okay, sometimes it might not be practical, but like researchers now are doing a great job in order to make things more practical. The other question is again how to kind of balance between privacy and utility. And again, this question is not only for differential privacy. It goes for all privacy mechanisms, as we have seen in k-anonymization and diversity and so on. And in particular, in this differential privacy is how much is the privacy budget? What is the value for epsilon, right? So there is no really an optimal value for epsilon. This is an open question, but it all depends on the amount of nodes that you add, basically by computing the the variance of the noise and so on, and the privacy. So the smaller the epsilon, the better the privacy, because that kind of gives us a bound on the probability ratio, right, between D and D prime and so on. And the other question, again, which is an open-ended question, is if we have a privacy budget, how should we manage epsilon if we have, let's say, an algorithm with many iterations and with so many things? Because why this is important? Because two things. We have a fixed privacy budget, and you know that if this privacy budget is smaller, the more noise that we add, right? So if we add more noise in the procedure, we might lose a lot of utility, right? But on the other hand, we gain a lot of privacy. And if we do the other way around, we're going to lose privacy, but we gain utility. So this is, again, this is an open-ended question. There are some tools and tips or guidelines to choose the privacy budget and manage the privacy budget for algorithms, but that's kind of, researchers started to kind of design a playbook or kind of rules for each algorithm, but that's kind of open for a lot of research. So this is kind of, I want you to go over this slide and understand it. You might have a question or two in the exam.
Doctor, do you do any change in the all the slides? So
well, very minimal changes, and not that much. I told you, like I usually find typos and so on. I fix it, but every time I fix it, I upload it to the Blackboard, to Teams, and so make sure that before you study for the exam, download the recent ones. Okay, but they are very minimal changes, and I don't change the whole slide from one version. Any question? So okay, I told you that this class will be mainly like a review. So before I go into the notebook, I would, I would go around a little bit and especially for those who did not participate in previous reviews, I would like to ask them to kind of share their answers about these questions. Okay. So the first question say, like in your own words. Don't tell me. Don't just read out the the formal definition. I want to know what is differential privacy in your own words. Okay, so I have a list here. I want to pick from. Okay, if they don't have an answer, then you can just raise your hand and answer me. See سعد الشمراني. موجود؟ سعد؟
Should we raise our hands?
دقيقة بس خلينا أمر عليهم بعدين. يحيى الثبيتي.
Yes, I'm here.
طيب, in your own words, okay? Again, don't read it from the slide. What is differential privacy?
It's privacy that guarantees like an individual privacy or record.
What do you mean by individual privacy?
Like in the table of records, each entity, the privacy of each entity is guaranteed.
Okay, so exactly. So that's kind of the overall objective of differential privacy. So I would ask you, how can we achieve differential privacy? How can we achieve differential privacy?
By the mechanism we just learned, like the plans.
Sounds good. طيب, عمار? عمار? Are you there? So my question to you, Yahya said, okay, by doing this Laplacian mechanisms, right? Sorry, Laplacian. In a nutshell, how does Laplace mechanism work?
Honestly, I don't have answer to that.
Okay. طيب, let's say مين في أحد رافع يده؟ أحمد, go ahead. طبعا مين ما في أحد رافع يده؟ عبد الله.
By taking the correct answer and add the noise.
Okay. By adding noise, what kind of noise? How do we get this noise?
By Laplace, by the Laplace distribution.
By Laplace distribution. Okay. شكرا. طيب. Okay. So Abdullah said, okay, by adding noise from Laplace. But he missed something. Okay, so he didn't give me the full answer. Let's see محمد القثمي موجود؟
Yes.
Muhammad. Abdullah said, okay, we're gonna add noise that is drawn from Laplace distribution, صح? But Laplace distribution takes two parameters, the mean and the variance. Okay? So what should be the mean and variance from that Laplace distribution?
That's not actually.
Right, Matt. So do you wanna think about the mean? So what does the mean in Laplace in any distribution? What do we mean by the mean?
The average.
Okay, and what is a variance? So it kind of shows you the you know, like the how does the shape of the distribution, right?
Yes.
So if you look in here in the slide, you see the red curve. This is a Laplace distribution with mean 0 and variance 1, or b is equal to 1. It's not really variance because variance here is 2b squared, right? But it's a kind of a function of the variance. So the mean it means that, you know, the average of this distribution is at the 0 point. If we shift it toward the left, like the green one, because we have mean is equal to -5, so the distribution will be centered around -5. And the variance means how wide is your, or how wide or how narrow is your curve, right? In this case, b is equal to 1, so it must be narrow. While in the green one, b is equal to 4. It might be wide, صح? So what is the difference between wide and a narrow distribution? I see Ahmed has raised his hand. Go ahead Ahmed. So هو يمكن السؤال ما كان قصدي بس إنه what is the difference between a wide and a narrow distribution? So if we have a small variance and a wide variance, a large variance.
The values of the database are closer to each other.
Okay. So in other words, the noise that we are adding centers around 0, right? So with large probability, we'll get values between 0, right? Between +1 and -1 with high probability. If it is wide, just like the black one, we have the amount of noise can be ranged from -2 to 2 with high probability. So this is what is probability distribution is about. Okay. By the way, Shabab, even if you don't have an answer and tell me I don't have an answer, that is fine. And again, it's not shaming you. It's just to kind of, you know, like review this material, and hopefully, if you don't have an answer now, you have an answer for that. Okay. I'll still count that for you in the participation. Let's say علي الجنبي موجود.
Yes, موجود.
Right. So we talked about 3 properties for differential privacy. One of them is post-processing. Again, in your own words, don't read it out from the slides. What do I mean by post-processing in differential privacy?
Actually, to be honest, I don't have an answer.
Right, okay. So who has an answer? Abdullah Nasser.
Yes, sir. Post-processing means that if we have a function that is differentially private, even if we do a computation on it, it will still differentially private.
Computation on what?
Like passing it to a function, for example, adding something, subtract something, it will still be differentially private, differentially private.
Passing what?
The algorithm, the randomized algorithm itself.
لا, passing the answer of the randomized algorithm.
Oh, the answer of the.
Yeah, I just want to be more technically correct, okay? That's exactly the point, okay? Okay, يعطيك العافية عبد الله. طيب just a minute. طيب خلينا نشوف يوسف الفارس موجود؟
موجود دكتور.
Another property we talked about is the sequential composition, right? And also we talked about parallel composition. So can you explain to me what is the difference between sequential and parallel? Again, in your own words.
It's like when you have the sequential of the queries add together, but in the parallel we send different queries. We like simulating the database in different tables.
Okay.
I mean,
and what is
like
okay? So you said separating database into different tables. Any restriction on such separation?
Can you ask the question again?
So you said you have to separate the database into different tables, right?
Yes.
Any
like
restrictions on this separation or group partitioning?
I'm not sure now.
Okay, Khalid. شكرا يوسف. Khalid.
They must be disjoint.
Disjoint. Okay, so there must be non-overlapping, right? Okay, so the last question, just for the sake of time, maybe we can we'll move on to something else. We talked about Laplace mechanism, right? And we said that Laplace mechanism works only for algorithms that give randomized numerical values, numerical answers. My question is, دكتور علي عبد الرب الرسول. علي موجود؟
Yes, sir.
My question is, can we still have differentially private algorithms for questions that does not return numerical values? For example, if we want to ask about what is the most common language in this class or second language in this class, obviously the answer is not 1, 2, 3. It has to be a language, right? Is there a mechanism, a differentially private mechanism, right, to kind of give an answer with some differential privacy guarantees?
I'm not sure, doctor.
طيب. Who has? I see Abdullah أنت جاوبت. Mahmoud.
Yes, doctor. Using exponential mechanism, we can retrieve some queries that are not numerical values using exponential mechanism.
Exponential mechanism, exactly. So, okay, Ahmed. What is exponential mechanism? No, I'm just kidding. It's obviously it's not included. So I'm not asking you about it. Anas, okay, I يعطيكم العافية شباب. So again, you see, again, this kind of question we just want to think about the questions, and it's also good measure for me to understand if the certain topics are already, or certain knowledge is already do you have it already or not? Okay, so it's really important to go on and review the knowledge or the concepts again from time to time. Okay. Okay. So let's go into the notebook. So I already uploaded that. Did I upload it? Did you see it?
Doctor, I think you duplicated the files.
Yeah,
for
you
1
did.
and 2.
Really? Okay. So
Yeah.
I'll upload the other one. Okay.
Okay.
Let me double check.
You upload to number 2 twice.
Number 2 twice. Oh, okay. So let me upload it now. So you can, if you have Jupyter Notebook, maybe you can also start working on it. Okay. Let me just upload it. So you can maybe download it and start playing with it. If you know how to run Jupyter Notebook, that is fine. Otherwise, you can check the installation document just to to give you an idea. Obviously you can Google it and so on, but I thought you are more than capable of doing so. You are already in senior year, and you are maybe better than me in finding the tutorial and then downloading stuff and setting it up. Anyway, so what is important here is I want to go through this tutorial to show you, or kind of give you an example of how differential privacy works. What do you mean by neighboring databases? How we construct queries, and can we run Laplacian mechanism in our hands, or is it just theoretical concepts, right? So hopefully after this tutorial and like this number 1 and number 2, you'll have a pretty good idea of how to run, or kind of how differential privacy can work, and then probably you might use some snippets of this code in order to solve homework 2. Make sense? Okay, so let us start. Okay, so obviously when we use differential privacy, or for this code, we need some libraries. Basically, we're going to use Torch because we need to use tensors and so on. So let's say here, okay. So what I'm doing here is I'm generating a synthetic database, a fictitious database. What is the simplest database that we can get? A bunch of 0 and 1s, right? So if we have it, and think about it just like having one column, and that column basically is, let's say we had this HIV, right? Positive and negatives. Positives are 1s, negatives are 0. So you have one column, right? And that column basically has 1s and 0s. So the way we do it, or the way I do it here, is by calling this torch function rand, and then I give it a number of entries. And obviously, so if you run this, let's say I run this alone. Okay. So obviously, this will give you 10 random numbers, and these random numbers are between 0 and 1. But we want to turn it into 0 and 1s, right? So the trick here is very simple. So I just check if that random number I got is greater than 0.5 or is less than or equal to 0.5, right? So if I run this again, I will get true and false, right? So this number is greater than 0.5, greater than 0.5, and so on. But if I want to have 0 and 1s, I will take the integer of the true and false, and that will return 0 and 1s, right? So let me do greater than 0.5. So I have now, of course, we have, because I specified 10, so number of entries, I will have 10 elements, an array of 10, or a tensor, I call it array of 10 elements. So I have 1, 0, 1, 1, 1, 0. And these are random. You see, if I run it again and again, I will have different values from one run to another. Make sense? So this is the database that I have, D. Now, from the definition of a neighboring database, what is a neighboring database?
With the one less with one less record.
If we removed one record, right? So the first neighboring database is by removing the first element, which is 0, right? And in Python, there is a way to do so by calling the same tensor starting from index 1. So we are leaving index 0 alone. Khalas, we don't care about it. So this is the neighboring database, and obviously it has how many elements?
9
elements, exactly 9 elements, right? So if you carefully look at the difference between D or DB, I'll call it, and DB prime, or one of the neighboring database, they differ in exactly one value of the first record. If you want to move the second entry, we're gonna use like some Python technique or kind of concatenation function that concatenate the first 2 elements with the rest of the elements. So in other words, I'm going to take, the first element and element from 1 to, element from 2 and go on. So what I'm doing is I'm going to call the first element, which is in this case 0, and I'm going to leave 0 out, the second element from the original database. I'm going to append the rest. Okay. So basically, this is the second neighboring database, and I will do that for all records, right? So what I'm going to do is I'm going to do a for loop. Okay, so what is that? Yeah, okay, so I'm going to do this. So what I'm going to do is I'm going to have a list, an empty list, and I'm going to do a for loop, right? That loops over every index in my array, and I'm going to call this function create neighbors. And basically, this create neighbors will take that index to remove and concatenate the rest of the tensors. So now I'm going to generate. So get this one first, and then. Okay. So now I have 10 databases or 10 neighboring databases. Okay. So obviously, if I want if you want to see it, you can do is. These are the 10 neighboring databases. So this is the first neighboring database. So let me just have DB here. So this is the original database, right? In the first neighboring database, I removed the first element, and the rest are the same. In the second neighboring database, I removed the second element, and so on, right? You can verify it easily. So what I'm doing is I'm creating a function here called create DB and neighbors, right? Where randomly, from time to time, I would like to call it in order to generate new databases for me. And of course, they will be randomized from time to time. Okay. So this is a function called create DB and neighbors. You will just give it how many entries do you want. So in here, let's say 100. So right. So I have a database of 100 elements. Okay. Obviously, it will take time to generate, but that is fine. Any questions so far? Okay, now comes the interesting point or interesting cases. If we want to do a count, تفضل خاطر.
Can you just explain the sensitivity count?
Okay, we'll go there. Okay, in a minute. Right. So in the count query, what we can do is, if we want to apply the count query on database, we can just count the number of ones, or kind of compute, or kind of, you know, like sum up all the elements. Okay. So what we can do is, I can call a function called dbSum. So we have that tensor db. I'll call the sum function. I'll get 4, and that is basically because we have 4 ones. 1, 2, 3, 4 ones, right? And if we want to compute let's say sum of all neighboring databases, I will just, you know, go over all the neighboring database and find, you know, the sum, and obviously some of them will have 3. Okay. So now we are interested in computing the sensitivity. So how do we do it? The way we do it is, I create a query called count query, which is basically return the sum of that tensor. Now this is the definition of a sensitivity. So sensitivity initially is equal to 0. Okay. What I do is, I'll take the database, or the answer of the original database. I'll take the answer of a neighboring database, take the difference between them, and that is the distance. So the distance between. I can't really.
You didn't run count query.
Yeah. Okay. So now the distance between the original database and the neighboring database, which is the first neighboring database, is 1. And you can't check that because, see, the first element is a 1. When we remove it, the count reduces from 4 to 3, right? But we are not only interested in this guy or in this neighboring database, we are interested in all neighboring databases, right? And you know how to do that using a loop, right? So what we're going to do is, we loop over all neighboring databases and we take the maximum sensitivity. Okay, so this is the function for having the maximum. So you'll not have any, I'm sure that you'll not have any problem in following up with this code. And in fact, see, I'm just showing you the difference between, let's say, tensor 3 and tensor 4, 1 and 0 and so on. If you take the maximum between all the sensitivities that you get is obviously 1, right? And this kind of makes sense because we said that any count query, we have a global sensitivity of 1. So we do it programmatically and get that result. So what I'm doing here is kind of, because I want to use the code, I turn it into a function. So this function basically takes a query, whatever query that you have, and the number of entries, and it will create a database and neighboring databases and compute the sensitivity. So okay, so if I run it, obviously it will create so many, you know, like from time to time it will create random tensors and compute the global sensitivity, and it's always 1. Right? There's only one case when the sensitivity will be 0. What is that case?
When you remove 0.
When all values are 0?
When all values are 0. If by random, some random, 10 values are all zeros, no matter what, who are you removing, the sensitivity will be 0, right? But that's kind of, you know, like a special case. Does that make sense? Right. Here we are. Okay, so so far, I was talking about a count query. Basically, you know, all the tensors. I want to create a new query, okay? Which is basically, it's a count query, but conditional count query. They call it threshold query. I will call it threshold query. And this query, basically, it will compute the sum. If the sum is greater than some threshold, right, then return true. Otherwise, return false. So this is a threshold query, right? So I'll create a database, a neighboring database, and I found that the sum is 6. So when I apply the threshold query on DB with let's say threshold 5, I'll get 1, right? So that is true. Now I want to compute the sensitivity of this threshold query. So what I can do is, let me do it this way. So this is the database that I have. I have 6, which is good. What is the sensitivity? It's 1, right? Now, let me run this for 10 other databases. So obviously the databases or the sensitivity will be different. So this is the first, let's say the first database with this is the global sensitivity is 1. This is another instance which has a sensitivity of 0. Why is that? Do you think? Do you know why in this instance of a database we have a sensitivity of 0?
Because we removed 0.
Because the database, the original database, has a count less than threshold, anyways, right? So the second database, the second instance, maybe has 4 ones or 3 ones, right? So my point here is that, you know, global sensitivity sometimes depends on what? Not sometimes, in general or all the time. Global sensitivity depends on what? The database that you have in hand, right? So as you see, for some databases, the sensitivity is 1. In some databases, the sensitivity is 0. So, and this is according to no free lunch theory, right? You need to analyze and understand the database or the dataset that you have in hand in order to control how much noise do you have, and basically, or are you going to add? And basically, that is done by you know, like computing the global sensitivity and then controlling the noise using, you know, a Laplace distribution or the function of the global sensitivity. Okay. See question Khaled, تفضل.
Doctor, in the homework, which query should we use? Is there a specific query should we use to solve the homework?
The count query.
For both the age and income and gender?
Yeah, so what you need to do is you need to adjust this query, right?
Mm-hmm.
Based on the, let's say, the range, the age range. Okay?
Okay.
Or what you can do also is partition the database into multiple partitions where each partition belongs to certain group of age, and then you call the count query on that partition or that table. Okay?
Mm-hmm.
So you're gonna do it, you know, like you have to tweak. Obviously, you have to tweak your code this code a little bit in order to, you know, like to get the answer for the homework. Make sense?
Makes sense.
Right. Now this is kind of, you know, so we talked about differential privacy, and obviously there is an attack. Although I did not talk about it explicitly, but I think I mentioned it you know, like kind of, I think 1 time or 2 times, which is called the differential attack or differencing attack, right? So differential privacy, basically, if you remove one table or add one tuple, right, from the table, and that is because if you run without, if you don't add analysis, you remember the blatant privacy, right? If you call a query by excluding one guy, that's called a differential attack. Okay, so basically, in other words, so let us do this database, okay, and there is create a neighbor. And let's say that we are calling what is that? Yeah. So this is the database, okay, or the sum of the database, and this is the sum of the neighboring database. Now, fortunately, you know, the both answer, the sum for the database and the neighboring database is 42. Although this neighboring database, we remove one guy from it. So there is no differential attack. However, if I, let's say, run this, let me create a new database. See, what I have here, I run some count query on the original database and I get 55. And when I run it on a neighboring database, I get 54, right? When I compute this, the difference, obviously the difference is 1. Now, if I know, for some reason, that the neighboring database that does not contain individual 1 or individual X, whoever that individual is, and I observe that the difference between the sum of DB and sum of NDB is 1, right? Then he must have that HIV disease or whatever, because the difference now is 1. If the difference is 0, right? So I wouldn't know that if that guy actually really has the disease or not, or if he was excluded from the database himself. So this is kind of the differential attack or the differencing attack. Basically, if you have the database, you query it, right? And then by somehow you query the same database excluding one tuple. If you were able to tell the difference between this answer, the first question, the second question, then you are kind of what's that? You are performing a differential attack. And that's why differential privacy, or what this kind of attack is, was differential privacy really is worried about, or kind of is concerned. Make sense? In the next, this is kind of how to achieve local differential privacy. And I already explained to you what is the difference between local and global differential privacy. An example of a local differential privacy is randomized response, basically by flipping the coin or flipping 2 coins at a time and so on. So what I can do here is, I simulate the experiment by flipping coins and then mask them together and then get the answers. Now, if you remember, there was a debate, or not a debate, but we contemplated about the utility of randomized response. We said, okay, if we are asking the respondent to flip a coin from time to time, what do analysts gain from this procedure, right? So we said that the amount of yeses or no's that you are getting after conducting the survey, you can estimate the original probability of people doing certain acts, right? And then I said that as you increase the sample size, that estimation is getting accurate, right? And now we can do so. We can show you that if I'm surveying this, obviously, if you can run all these. So it's easy to follow. Basically, I'm simulating this coin flips. If he's getting head, he will tell the truth. If he's getting tail, he's gonna flip another coin, and so on. And then I'm interested in finding the mean. Okay, so this is kind of the function. Now, if I do the randomized response with 10 respondents, the noise or the mean with the noise is -0.3. Without noise is actually 0.2. So without noise is the actual mean, or the actual number of people, average number of people that are actually doing some act. And this is with noise. Obviously they are far away, right? In another survey, they are exactly matching. But if you run it multiple times, you'll see that there are some differences, right? And this is expected because it's all probabilistic in a sense. But however, if we increase the size of the sample, we see that the difference between them start to shrinking, right? There's a difference, but it's shrinking. If we also increase the sample size, the estimation or the estimator and the correct value start to kind of match each other. And obviously, if you run it, no matter how, of course, the value itself will be different because we are making, we are surveying, kind of conducting a survey of different group of people. But what matters is the difference between the mean with the noise and without noise. Sometimes you'll get high, but on average, they match each other. Obviously, if you increase the sample size more, it will take time, but they are approaching each other. So in other words, what the point here is, if you increase the sample size, the number of people that you are asking, the estimation to get the correct percentage of people that did some shameful act or whatever, getting more accurate, right? And this is called randomized response. This is a local differential privacy. which is kind of because it's each respondent will do his will add his noise locally, independent from other respondents. And this is basically the global differential privacy or Laplace mechanism. And the whole point here is, or the main point is, this function here. So I'm using a tensor function called NumPy function called NP random.Laplace. And I'm passing three things: 0, mean 0, beta, which is sensitivity divided by epsilon, and 1. Basically, this is kind of the forgot what is that. I think it's kind of upper bound in the Laplace distribution, but you always. But the main important thing is that 0 is always, you have always 0, and 1 is always 1. Beta is what is different, and beta you calculate it based on sensitivity of that function divided by epsilon, which is privacy budget. So in this case we have 0.1. Let's say I want to find the number of counts on my database, and then we'll add Laplace mechanism, or kind of like run that randomized mechanism. And obviously you see this is the count, which is 47, which is less than 62, because the amount of nodes that we are adding, right, can be either positive or negative. But if you run it multiple times, see, it will add different amount of nodes. Now, if I add, obviously 0.1 is a relatively large number in terms of privacy budget. We always recommend you that epsilon to be low or small in order to preserve the privacy or have that probability bound closer to 1. But what happens here is that we add more noise to the original answer. Sometimes it's way off, right? Now, yes, the utility here is bad, but if the user or if the analyst is running this many times, right, many times, and he kind of construct this probability distribution of all the answers that he's getting, the probability that he runs this question on the original database and any D prime, right, will be bounded by e to the power epsilon. Make sense? So again, this is kind of the essence of differential privacy, is to bound the probability of running randomized mechanism or function on D and D prime. The ratio of the probability should be bounded by e to the power epsilon. So I leave this up to you to go over. If you have any questions, obviously I'll be available on Tuesday. So although we don't have class, but I'll be kind of conducting office hours. If you have questions regarding this or regarding like preparation for the exam. In the second DP tutorial, what I'm doing here is making the database a little bit more advanced. Rather than having only 0 and 1s, I'm creating a database of with elements between 0 and 100. Okay, so basically this is the database that we have. So I should run all of them, and then I'll conclude. So I'll just show you what I'm doing here, and then I will conclude. So this is my database. Obviously, it will not conclude. It will not have 0 and 1s, but it will have real numbers or integer numbers between 0 and 100. Now, if I want to compute the sum, obviously the sum is not the sum of 1s, right? Okay. Now, if I want to compute the sensitivity is always, obviously, is 100. Why is 100? Why the sensitivity is 100?
I think the maximum number in the database.
Exactly, because when I draw the values, right? The range of the values is between 0 and 100, A and B. So right. So the sensitivity of the global sensitivity of the Kant query in this case is 100. So again, go back to the assumption. You have to analyze your database in hand in order to adjust the amount of nodes that you have. And then obviously I'm doing a little bit more, like more advanced queries, like mean queries. I can compute its sensitivity. So the sensitivity of a mean query, I think here is a problem. I don't know why, but anyways. So you see, basically I'm computing the, yeah, absolutely. Play with it in your own time, and I'll try to fix this. Anyways, I think this is the. Okay. So DB, anyways. Okay. So you can see, at least you can have a sense of how to apply Laplacian mechanism, and how actually you can actually develop a Laplacian mechanism in your own. So I'll stop here. If you have any questions, you can ask me now.
Doctor, how is the midterm exam questions is going to be?
Good question. It will be like more or less like quizzes, but I might like also use some short answers questions, short essays. So I'll ask you to write some short answers. Now, the one that I'm not sure about is how are you gonna type equations if there are any. Okay. So I might ask you to kind of if you have a Scratch. So anyways I'll upload the question in two forms: the question like a soft copy of the exam, and I will turn it into like a Blackboard questions. Let's say for those multiple choice questions and multiple answers and so on, you can obviously do the Blackboard. For the written question, you can either type it or you can just write it on a scratchpad, or maybe print the exam and take a picture and then scan it for me later on. So I can grade it. Okay, I'll give you the details, inshallah. So the exam is on Thursday. I'll give you the entire details on Tuesday, or maybe on before the exam, definitely.
Sir, about this homework, is it possible to delay by 1 or 2 days?